the output of matched filter. So yt can be written as the input xt convolution with the impulse response. So that will be the output of the matched filter, and ht already determined. Xt depend on the signal choice, input signal choice. Now if I assume, let's consider a case that xt is a rectangular pulse with t duration, that is xt, and from the theory of matched filter we know that input and the match filter response, that is impulse response, will match. So filter response will match each other, so that will be ht, and their convolution, if I convolve ht and xt to rectangular identical pulses, convolution will result a triangular kind of pulse, that is yt. Okay, and that maximum value will be a square into t, and at the time t it reaches the maximum. So here we are taking the sample, so input signal having maximum value at t, so that's why signal to noise ratio will give you maximum value. So next we shall discuss the correlator, another kind of receiver, correlator. In this case it is different from match filter processing. In this case you have noisy input signal which can be represented by ft equals xt plus nt, that is our noisy input signal, and at the receiver side we'll multiply it by a locally generated signal xt. So at the receiver side we'll multiply it by a locally generated copy of the xt, and result will be ft into xt. Then we shall integrate this multiplication over the time interval 0 to t. So we'll integrate, so that will be integrator. After integration you have output yt, and we'll take sample of the output at time t equals t, so it will be y capital T. So that will be the correlator, and yt, that correlator output yt is 0 to t ft into xt dt. Now we shall consider the case, we will consider or compare this correlator with match filter. Now we know that match filter output, similar way we can visualize match filter output. If I apply the same input, noisy input, to a match filter output, so match filter, and we'll take, that will be yt, some yt, and we'll take the sample at time t equals t, so it will be y capital T. So we'll do the same process for the match filter and see what will be the response. So yt will be here, y small t equal ft convolution, so filter response is ht convolution with ht. So yt is convolution of input noisy signal and filter response. It is equal to minus infinite to infinite f of tau h of t minus tau d tau. Now we know ht equals 2k by n0 x of t minus t. So ht we know, we'll find out ht minus tau. So ht minus tau, it will be 2k by n0 x of t minus see here we replaced tau we replaced tau by t minus tau, so that's why it is uh, negative and positive. And we'll replace this into yt expression, so y small t will be minus infinite to infinite f of tau 2k by n0 d tau. Now at time t equals t, we are taking the sample. Before that, we know the bit duration is t. We know the bit duration t. So this f tau will be valid for 0 to t. F tau we are taking for 0 to t. So integration limit will be yt equals 0 to t f tau 2k by n0 x of t minus t plus tau d tau. Now we are taking sample at t equal capital T. T will be capital T. So y capital T equals 0 to t f tau x t minus t plus tau d tau and yt 2k by n0 0 to t f tau x tau d tau. Now we can write t instead of tau. So yt equals 2k by n0 0 to t ft xt dt. So that is the match filter output at time t equals capital T, and the correlator output was yt equals 0 to t ft xt dt. So that is correlator output. So that is for correlator and that is for match filter. Now if we assume 2k by n0 is normalized to 1, then correlator output and match filter output will be equal. So in either methods we can achieve the optimum performance, and that's how any of these two can be used for the communication receiver. Thus we can write match filter and correlator are two different techniques which gives same result. Any of these two techniques can be used to synthesize the optimum filter.